If oil powers nations, uranium offers something far more terrifying: the potential to alter the global balance of power. It is one of the most dangerous materials ever mined, an element capable of powering an entire city for years, but also capable of destroying it in seconds. So how do humans find uranium, extract it from seemingly worthless rocks, and turn it into fuel for nuclear reactors or the world's most powerful military systems? Let's find out in today's video. The importance of uranium lies not in its commercial value, but in what it has changed in human history. In 1945, the world witnessed the true power of this element for the first time when the uranium bomb known as Little Boy was dropped on Hiroshima. In just seconds, a city was almost completely wiped out and humanity entered the nuclear age. Since then, uranium has ceased to be simply a mineral found underground. It has become a symbol of national power, military technology, and strategic authority. After World War II, the great powers engaged in the largest nuclear arms race in history. The United States, the Soviet Union, Great Britain, France, and China all invested enormous resources to control uranium resources and develop nuclear enrichment technology. During the decades of the Cold War, tens of thousands of nuclear warheads were built, creating a fragile balance between the superpowers. Because of its unique role, uranium has been called the oil of the 20th century by many strategists. If oil determines economic and industrial power, then uranium has become the foundation for nuclear energy, nuclear submarines, and strategic deterrence capabilities. The journey of uranium begins deep beneath the ground in northern Saskatchewan, Canada, home to some of the richest uranium deposits on Earth. Here, uranium ore bodies lie approximately 1,500 to 1,700 feet below the surface, surrounded by ancient rock formations that were created billions of years ago. But before miners can even reach the ore, engineers must solve a dangerous problem: high-pressure groundwater. If left uncontrolled, water can flood the tunnels at any moment, causing collapses and bringing mining operations to a halt. To prevent that from happening, they use a solution that sounds more like science fiction than mining. More than 200 steel pipes are drilled around the ore zone, and a cooling solution at approximately -22 degrees Fahrenheit is pumped underground. Over time, the surrounding soil, rock, and groundwater freeze into a massive shell of ice, creating a stable protective barrier around the deposit. Only after everything is secured can drilling begin. Remote-controlled drill systems equipped with ultra-hard tungsten carbide bits cut through the rock and precisely target the uranium-bearing zone buried deep below the surface. Once the uranium ore has been separated from the surrounding rock, it begins its journey out of the mine. Deep underground, trains made up of 10 to 20 ore cars travel continuously along dedicated rail lines through a maze of dark tunnels. Each car can carry several tons of ore, and the system operates nearly 24 hours a day to maintain a steady flow of material. Day and night, these underground trains move uranium-bearing rock from the mining areas to central collection points, creating a constant stream of raw material destined for the next stage of processing. Once the ore reaches the surface, it is still nothing more than ordinary rock. Although uranium is present inside, most of it remains trapped within the mineral structure, making extraction nearly impossible unless the rock is broken apart first. The process begins with large chunks of ore passing through industrial crushers, reducing them to pieces roughly 2 to 4 inches in size. The material then moves through several stages of grinding, becoming finer and finer with each step. Finally, the crushed ore is mixed with water to create a thick slurry containing approximately 40 to 50% solids. At this point, the uranium-bearing rock is no longer a pile of stone, but a flowing material ready for the next stage of uranium extraction. After being ground into a fine powder and mixed with water, the uranium ore enters the extraction stage. The slurry is pumped into large processing tanks, where sulfuric acid is added to dissolve the uranium from the surrounding material. For several hours, powerful agitators keep the mixture in constant motion, ensuring that every particle comes into contact with the chemicals. What makes this process remarkable is that the acid does not dissolve everything. Instead, it primarily targets the uranium, transferring it into solution while most of the rock and other minerals remain solid. Once the reaction is complete, the uranium-rich solution is separated from the remaining waste material. This concentrated liquid can contain as much as 80 to 90% of the uranium originally present in the ore. Once the uranium has been dissolved into solution, the next goal is to recover it in solid form. Through a carefully controlled combination of heat and chemical reactions, the uranium gradually precipitates into tiny particles that settle to the bottom of the tanks. This material is then separated and dried, producing a yellow-brown powder known as yellow cake. A standard 55-gallon steel drum can hold thousands of pounds of yellow cake, enough to continue through the later stages of nuclear fuel production. Despite being traded around the world as a strategic commodity, yellow cake looks surprisingly ordinary. Unlike what movies often suggest, it does not glow or emit visible light. It is simply a powder that contains the raw material for one of the most powerful energy sources ever used by humanity. After being processed into yellow cake, uranium is still not ready to be enriched or used in a reactor. Before the next stage can begin, it must be converted into a gas. Through a series of chemical reactions, the yellow cake is transformed into a compound known as uranium hexafluoride. What makes it unique is its ability to become a gas at approximately 133 degrees Fahrenheit, a relatively low temperature compared to most metal-based compounds. Next comes the most sophisticated stage in the entire process, enrichment. In nature, only about 0.7% of uranium exists as uranium-235, the isotope capable of sustaining a nuclear chain reaction. That percentage is far too low for efficient use in most commercial nuclear power plants. To solve this problem, uranium gas is fed into high-speed centrifuges that can spin at up to 50,000 revolutions per minute. Inside these machines, tiny differences in mass between uranium isotopes are gradually separated. The process is repeated through hundreds and sometimes thousands of centrifuges connected in long cascades. After many stages, the concentration of uranium-235 is increased from 0.7% to roughly 3 to 5%, making it suitable for use as fuel in modern nuclear reactors. Once enriched, uranium is no longer kept in its gaseous form. The uranium hexafluoride is cooled and converted back into a solid before undergoing additional chemical reactions to produce uranium dioxide, the standard material used in nuclear fuel. At this stage, the uranium appears as a fine black powder rather than the invisible gas used during enrichment. Every batch is carefully tested for purity, particle size, and chemical composition to ensure consistent quality. These checks are critical because even small variations can affect fuel performance inside a reactor. Only after meeting strict specifications can the material move on to the next stage of fuel manufacturing. The uranium dioxide powder is pressed into molds under enormous pressure, forming small fuel pellets that are only about half an inch long. Once shaped, the pellets are heated to approximately 2,900 degrees Fahrenheit in a process known as sintering. This extreme heat removes any remaining voids and bonds the material into a dense, solid structure. The result is a fuel pellet with a hardness similar to industrial ceramics, capable of withstanding the intense temperatures, pressure, and radiation found inside a nuclear reactor. Though small in size, these pellets are engineered to operate reliably for years while producing enormous amounts of energy. After they are manufactured, the fuel pellets still cannot be loaded directly into a reactor. Instead, they are stacked inside tubes made from zirconium alloy, a material that can withstand extreme temperatures while absorbing very few neutrons. Once the tubes are filled, both ends are sealed to create complete fuel rods. Each fuel rod contains hundreds of pellets arranged in a straight line and is designed to operate reliably under harsh reactor conditions. However, these rods do not function on their own. They are assembled into fuel bundles consisting of dozens of rods positioned side by side and held in place by precision-engineered support structures. These bundles are the final form of nuclear fuel before they are loaded into a reactor core. But the journey of uranium does not end here. Once assembled into fuel bundles, they are loaded into the reactor core, where nuclear energy is finally released. Inside the reactor, uranium-235 atoms split apart in a process called fission, releasing heat and additional neutrons that trigger more fission events. This chain reaction generates an enormous amount of heat, raising the temperature of water to approximately 570 degrees Fahrenheit under extremely high pressure. The resulting steam is then directed toward massive turbines spinning at thousands of revolutions per minute. Those turbines drive equally massive generators, converting the energy stored inside uranium atoms into the electricity that powers homes, businesses, and entire cities. From rocks buried deep beneath the Earth to fuel capable of powering entire cities and nuclear submarines, uranium is proof that some of the most ordinary-looking materials can possess extraordinary power. If you enjoyed this video, be sure to leave a like, share your thoughts in the comments, and subscribe to Mido Explained for more fascinating stories about the hidden systems that keep our modern world running.